Okay. Hi guys, I'm going to introduce you to ANOVAs really quickly. So ANOVA stands for Analysis of Variance, which some people find a little bit intimidating, but it's actually quite simple. So I'll just try and explain it to you really briefly. So with ANOVAs you have one metric DV and one or more categorical IVs. We're going to start by learning about ANOVAs with just one IV. The IV can have two or more groups. Generally, if you've got two groups, you'll use an independent samples t-test, but you can use an ANOVA if you want. But an independent samples t-test can't analyse anything with more than two groups in the categorical IV, whereas ANOVAs can. So there are different sources of variance that can be measured. So you can divide the total variance up into the variance within each of the three groups of the categorical IV and the variance between each of the three groups in the categorical IV. And so the variance within each group is considered the background variance, or the variance that's due to nuisance variables. So within each group, all the participants within one group have experienced exactly the same treatment effect. And the only reasons their scores differ from each other within that same group is due to individual differences and background other nuisance variables. So the variance within each group is considered the background variation, whereas the variance between each group is due to the treatment effect. So if the variance between each group is greater than the variance within each group, then the conclusion is that there is a treatment effect. However, we need to see whether this difference is large enough, whether the variance between each group is it might just be, every time you take a sample, the mean will differ. So the difference in means between the groups might just be due to random sampling variance, because every time you take a sample, the score differs. So you need to see if the difference between the groups is sufficiently large to conclude that it's due to the treatment effect. And the way we do this is by calculating a ratio called the F ratio. And the F ratio is the ratio of the variance between the groups over the variance within the groups. And if this is sufficiently greater than 1, then we can conclude that the p-value will be significant and there is a treatment effect. So I'll show you this through the slides. So just as a reminder, variance is the sum of the squared differences of scores from the mean. So when we take a sample, we take the mean of that sample, but we also want to know how much the scores differ from the mean. If we took the average difference of each score from the mean, it would be 0, because the definition of the mean is that the scores either side of it will add up to 0. So to get around this problem, in order to take a measure of the variance of scores about the mean, we square their difference from the mean and we sum this together. So variance is the sum of the squared difference of scores from the mean, which is represented like this. There's the score minus the mean squared and summed together. That little e just means sum together, the sum of the squared differences of the score from the mean, the scores from the mean. This is also called the sum of squares. Okay, sum of squared differences from the mean, or sum of squares, represented as SS in the notation, and then if you divide it by the degrees of freedom, it's MS, or the mean sum of squares. And the F ratio is actually the mean sum of squares, is used for the F ratio. Okay, so the sources of variance. So as I mentioned before, there's total variance, and you can divide the total variance up between to the within group variance and the between group variance. So the total variance is the squared difference of each score from the grand mean. The grand mean is the mean of all of the participants in the group, in the sample. So forget about each group. If you take the mean of all of the participants in the sample, it's the grand mean. The total variance is the squared difference of each participant's score, or each case's score, from the grand mean. The sum of the squared differences, I should say. I'm just simplifying it. So the within groups variance is the sum of the squared difference between each score and their group mean. So as I mentioned before, the dispersion of scores within a group around that group's mean. So the sum of the squared difference between each score and the group mean. Between groups differences between groups variance, is the sum of the squared difference for each participant, the sum of the squared difference between their group mean and the grand mean. Okay? So if you look at this as a graph, you can see if this is the participant score, their total variance is the deviation of that score from the grand mean, and that is made up of the deviation of that score from their group mean and the deviation of the group mean from the grand mean. So that is the partitioning of variance. So we divide the total variance into these sources of variance, the within groups variance and the between groups variance. And if we add it together and we find for the whole sample that the between groups variance is greater than the within groups variance, then we conclude that there's a treatment effect, and I'll explain a little bit more why. So the variance within each group, the variance within the groups is attributed to nuisance variables, as I was just saying. It's termed background variation. So as I mentioned before, because within one group, all the participants in one group have experienced the same treatment effect. So ideally, if there was no nuisance variables and no individual differences, they'd all have the same score. But because there are nuisance variables and there are individual differences, the scores will differ within a group. And that's considered a measure of background variation because it's the variance that's not attributed to the treatment effect. It's variance that's attributed to individual differences rather than the treatment effect. And because every time you take a sample from a population, you'll get a different set of individuals, the mean will always be different. So when you're comparing the means across the three groups, you want to know whether it's just they differ just because you've taken a slightly different sample, obviously, or whether they differ due to the treatment effect, and you examine that through a ratio. So the variance between the groups is attributed to the treatment effect. So it's a measure of the treatment effect. There's also a bit of nuisance variables in there, but it's also a measure of the treatment effect. So if the variance between the groups, the treatment effect, is greater than the variance within the groups, the background variation, there is said to be a treatment effect. So the F ratio, the ratio of the variance between the groups over the variance within the groups is how we decide whether there is actually a treatment effect. So it's not actually, instead of the sum of squares, it's the mean sum of squares. So we divide the sum of squares between the groups by the degrees of freedom, which I'll show you in the next video, and we divide the sum of squares within the groups by the degrees of freedom to get the mean sum of squares between groups over the mean sum of squares within groups. Hence the F ratio is a ratio of the treatment effect to the background variation. If it is less than 1, then there is no treatment effect. And if it is sufficiently greater than 1, then there is a treatment effect. We conclude that there is a treatment effect. So the way that we do this is actually covered in your textbook, but in order to determine whether we can conclude that the F ratio is sufficiently greater than 1 for us to conclude that there is a treatment effect is by comparing it to what's called an F distribution. So F distributions differ for different sample sizes, but basically if you were to take lots and lots of samples, say if you take 3 samples over and over again, so if you were to take lots and lots of samples and there was no treatment effect, you would have, every time you take a sample you get a different mean, and if you were to graph that mean you'd get what's called an F distribution. And if there was no treatment effect and you calculated the between groups variance over the within groups variance, you'd mostly get really small F ratios, but very occasionally you get large F ratios. So if you get an F ratio that is so large that you'd only get that F ratio 5% of the time or less, then you would consider that, you would conclude that that F ratio is unlikely to have occurred unless there was a treatment effect. It would only occur 1 in 20 times without there being a treatment effect, and so that's considered sufficiently unlikely to occur just by random chance for us to conclude that there is a treatment effect. So this is the same sort of reasoning as you learnt in first year. So that's using a p-value of 0.05. If you achieve an F ratio that has 5% chance or less of occurring when there isn't a treatment effect, then we conclude that there probably was a treatment effect. It's probably occurred because there is a treatment effect. And that's the end. And now I'll do another little video on calculating the F ratio.